when we solve a system of linear equations, the way we do that is by taking the equations and doing some manipulations to those equations. For example, adding a multiple of one row to another. We know what the effect of doing that is on the corresponding augmented matrices. The effect is row operations. But we have a little bit of a problem here. The idea is usually to actually solve these equations, so we do a bunch of manipulations and hopefully we end up with the equations in a really simple form from which we can read off the solutions. But how do we actually know that when we did those manipulations we didn't change what the solutions were? So how do we know that the set of solutions to the nice simple equations at the end of our manipulations are the same as the set of solutions to the equations we started off with? That's what we're going to look at the beginning of this lecture. What we'll do is prove the following theorem, which informally you could summarize by saying row operations don't change the set of solutions to a system of linear equations. Stated formally, what the theorem says is, suppose that you have a matrix, or an augmented matrix, which I'm writing as A prime B prime, which arises from doing a sequence of row ops to the augmented matrix AB. Then the set of solutions to the matrix equation that you ended up with is the same as the set of solutions to the original matrix equation AX equals B. In order to prove this theorem, it's enough to do the case where the augmented matrix A prime B prime arises by doing a single row op. Because if doing one row op doesn't change the solutions of the corresponding matrix equation, then doing one row op doesn't change it, so doing another row op doesn't change it either, so by doing any sequence of row operations won't change the set of solutions. Luckily for us, we know about the effect of row operations on a matrix. We know we can express that effect as being the same as multiplying on the left by an appropriate elementary matrix, and that's going to be the thing that we use to make the proof work. Let's talk through the proof now. As I said, it's enough to do the case when A prime B prime arises by doing a single row op R to the original augmented matrix AB. So in that case, because of the way row operations work, A prime will be the same as R of A, and we know that doing a row operation R to A is the same as multiplying A on the left by the elementary matrix R of I. Equally, B prime will be R of B, and of course that will be the same as multiplying B on the left by the elementary matrix R of I. Now, let's suppose we have a solution. Well, let me put this slightly differently. Let's suppose we have a vector V. Then I claim that AV is equal to B if and only if R of I times AV is equal to R of I times B. And in fact, that's an if and only if, so both directions. The reason that if and only if is true is because if this equation holds, then certainly this equation holds too, because you obtain the second equation just by multiplying on the left by R of I, the elementary matrix. On the other hand, the elementary matrix R of I is invertible. And so if this second equation is true, then you can get back to the first equation by multiplying on the left by the inverse of R of I. So that's why the first equation is true if and only if the second one is true. You can go from the first to the second by multiplying by R of I, and you can go from the second to the first by multiplying by the inverse of R of I, which you know exists because we proved a theorem that said elementary matrices are invertible. Okay, so AV is equal to B if and only if R of I times A times V is equal to R of IB. And that's true if and only if A prime V equals B prime, simply because A prime equals R of IA and B prime equals R of IB, as we established earlier. So what these two if and only ifs are telling you is that V is a solution of the matrix equation AX equals B, if and only if it's a solution of the matrix equation A prime x equals B prime. And that tells you that the set of solutions for our first matrix equation, Ax equals B, is precisely equal to the set of solutions for the matrix equation A prime x equals B prime, which arose from doing a single row operation. Right. So to summarize then, doing row operations to the augmented matrix for a system of linear equations doesn't change the set of solutions to that system of linear equations. So this is terrific news because it means we can use row operations in order to solve our systems of linear equations, and it means that we can use the strategy of starting off with our augmented matrix AB, which may be very complicated, it may be very difficult to see what the solutions of the corresponding linear system are, and we can now do a load of row ops until we get that system into a simple form from which we can read off the solutions. And then we'll know, because of this theorem, that in doing these row ops we haven't changed the solutions to the system. So the solutions to our nice simple system, which we've got by doing a bunch of row ops, are the same as the solutions to our original system of equations. So the question arises, what nice simple form can we aim at? What is the nice simple form for a system of linear equations which we can reach by doing a bunch of row ops? And the answer is called row-reduced echelon form. Here's the definition of row-reduced echelon form. Actually, before I can define it, I need to define something else, which is what's called a leading entry. So the definition is that a leading entry, or LE for short, in a matrix is the first non-zero entry in one of the rows of the matrix starting from the left. So looking at this example here, in this matrix here, the first row has a leading entry, which is that number 2 there. That's the first non-zero entry in that row starting from the left. On the other hand, the second row doesn't have a leading entry at all because all the entries in the second row are 0. Now we know what a leading entry is, we can define row-reduced echelon form. A matrix is in row-reduced echelon form, or RREF for short, if it satisfies all 4 of the following conditions. Firstly, all of the leading entries in the matrix must be 1. Secondly, if there are any 0 rows in the matrix, in other words, if there are any rows all of whose entries are 0, then those 0 rows have to be at the bottom of the matrix. You can have more than one 0 row if you like, but all of the 0 rows must be at the bottom. Condition 3 is that every entry which is in the same column as a leading entry must be 0. So if you've got a column which contains a leading entry, every other entry in that column must be 0. Finally, condition 4 is that if row I and row I plus 1 have a leading entry, then the leading entry in row I plus 1 is to the right of the leading entry in row I. So as you go down the rows of your matrix, the leading entries must go to the right. Let's look at some examples then. I've copied at the top right of this slide the definition of row-reduced echelon form, and we're going to look at some example matrices and why or why they're not in row-reduced echelon form. The first example here is not in row-reduced echelon form. If you like, you can pause the video now and think, why not? Well, the answer is it's not in row-reduced echelon form because it has a row of zeros, and that row of zeros is not at the bottom of the matrix. And if you look at condition 2 in the definition of row-reduced echelon form, that says that any 0 rows must be at the bottom of the matrix. Okay, matrix 2 here is also not in row-reduced echelon form. Again, you might pause the video and think about why. If you did that, I hope you came to the conclusion that the reason this is not in row-reduced echelon form is because it doesn't satisfy the first condition. It has a leading entry right here, and that leading entry is not equal to 1, so it's not in row-reduced echelon form. Example 3. Again, think about why this is not in row-reduced echelon form. Maybe pause the video. If you did that, then you will have concluded that this is not in row-reduced echelon form because of condition 4. Condition 4 says that if row I and row I plus 1 have a leading entry, the leading entry in row I plus 1 has to be to the right of the leading entry in row I. And what you can see here is that the leading entry in row 2, just there, is not to the right of the leading entry in row 1. In fact, it's strictly to the left of the leading entry in row 1. So it's failed condition 4. Next, let's think about a more complicated example. We're going to think about the example just here. In this example, I'm thinking of alpha and beta as being certain numbers. And whether or not this matrix is in row-reduced echelon form depends on the value of beta. Specifically, it's in row-reduced echelon form if and only if beta is equal to 0. The reason for that is that this matrix satisfies conditions 1, 3, and 4 no matter what alpha and beta are. But it doesn't satisfy condition 3 unless beta is equal to 0. If you take a look at condition 3, what it says is that all of the entries in the same column as a leading entry must be 0. Now there is a leading entry just here in row 2. The leading entry in row 2 is 1. It's in column 3. And in order to meet condition 3 of the definition of row-reduced echelon form, every other entry in that column must be 0. So beta, which is an entry in the same column as the leading entry 1 in row 2, must be 0 for that matrix to be in row-reduced echelon form. Just checking quickly, this matrix does meet all of the other parts of the definition of row-reduced echelon form in every circumstance. Right? The leading entries are here and the one that I've already highlighted, and those leading entries are equal to 1. There are no 0 rows at all, so condition 2 doesn't apply. And condition 4 is that the leading entry in row 2 has to be to the right of the leading entry in row 1, and that's true. The leading entry in row 2 is in column 3, so that's to the right of column 1, where the leading entry in row 1 lives. Finally, looking at our last example here, this matrix is in row-reduced echelon form. It satisfies all 4 conditions. Firstly, the leading entries are here and here, and those leading entries are equal to 1. Let's just get rid of those highlights because they make it a bit hard to read. Secondly, all the 0 rows are at the bottom. There's a row of zeros, but it is the bottom row of the matrix, so that condition is satisfied. Next, all the entries in the same column as a leading entry are 0. So you can see that the only leading entries are here and here, and the other entries in those columns are 0. Right? There are zeros here, there are zeros here, and there are zeros here. So condition 3 is also satisfied. And finally, condition 4 is satisfied because the leading entry in row 2 is to the right of the leading entry in row 1. That condition doesn't apply to rows 2 and 3 because there is no leading entry in row 3. So it's satisfied completely. All of the 4 parts of the definition are satisfied, and therefore that matrix is in row-reduced echelon form.